with why we make this assumption. It's this exercise. Yes, we have a universe that's filled with matter. Doesn't have to be the mysterious dark matter, just any matter that has gravitational interaction. And my claim is then take the Friedmann equations, which holds for all kinds of gases that you put in there, so also a gas of matter. And my claim is, well, then you can take rho, its density, to be 1 over the scale factor to the power 3. Why is that? Yes?
Well, this now we were thinking, since rho is like density, so it has to have like the unit of a volume maybe, and since A is like distance over 3 is the volume.
Yes, well that's all there is to it.
Can you define what A was again?
It's a scale factor. It's the amount of distance between 2 points in space.
Yeah, okay.
And a volume is a distance in space in 3 directions. So that's a to the power 3. So if you know that this is a density should be an energy divided by the volume in which the energy is in, then that should give you 1 over a to the power 3. Of course, the number on top here is, of course, should be the energy within that amount. Energy is... Sorry?
That's why we were not really sure, because we thought like maybe something about a mass over volume. So
oh well, well, mass and volume. Mass and energy only differ by a factor of c squared.
No, well, we were looking in the formula itself if units cancel out and give.
Oh, I see. Yeah. No, I understand, but I'm just going to give this a number. Might as well call it energy. And we will find it's not really important for the conclusions that we're going to draw. Need some. Let me remove this. So yeah, we're going to put that in, and I'm also going to put in that the pressure of this gas is 0. Any ideas on that? Why that would be the case?
Because we're talking about the cold energy.
Yes.
All the particles within the universe would have no kinetic energy and therefore not exert any pressure.
Yeah, that's good enough. Yes. I mean, the whole idea that if you have a gas and it's cold, there's only a small amount of energy, and you, in a literal gas, the energy of the gas is a measure of the average kinetic energy of these things. That means that they do almost no pushing. Now, it so happens that you don't have to assume this as a separate thing. At the moment that you plug this in, this will come out mathematically. There's a reason for that, and that has to do with the conservation of energy. We haven't talked in full detail about the Einstein field equations. I'll be there in a second. But if you take the Einstein field equations, right, the one that connects the curvature of space to the amount of energy, then you can show, or not just show, it's actually physically built in, that this tensor that gives you the energy is conserved. Here's the expression. I mentioned this to Lizzie, I think, during one of the breaks. But there was this tensor, right, which gave you the energy. And my claim is that in general relativity this holds. There's a caveat, I will put that in a second. And if you recall, there's a contraction here, there's a mu upstairs and downstairs, so that this really means the time derivative of this thing with the time here, plus the spatial derivatives of that thing with the spatial components, and another one for y, another for z, this whole thing should be 0. And at least the electrodynamic people should view this thing as familiar.
Something with divergence.
Yes, let me write it like this. This part you can also write as a divergence of, well, this thing. It's not really a vector, but let's write it like this. In electrodynamics we call this a continuity equation. Because back then we had an equation like this. There's a time derivative of the charge, excuse me. The time derivative of charge plus the divergence of the current is 0. That if you see charges moving away here, as in 1 second later there's less charge here, that it must have moved through space. That was the continuity equation from electrodynamics, and in relativity there's a similar type of equation for the energy density. And then you will find that this is the energy and this is the momentum. It just says if you see that there's energy missing here, then that means something has moved through space. You have lost momentum. And they have the same sort of connection to each other as do charge and current. Now why do I tell this? Because if this thing, the conservation of energy, because really that's what it says. It says if you're missing energy here, it has moved away through space. That's what it says. If you have this in general relativity, then you should also have that rho and p are connected to each other. Because p is really the moving away of rho. It's probably not in the way that you've heard it by thermodynamics, but this is what it is. So all I'm saying is that in the Friedmann equations, which came from the Einstein field equations, you should also automatically have built in the conservation of energy. So at the moment that you assume something like this, then automatically it should give you what the corresponding P is. That's what I'm saying. It's a little involved to get that out, so this I'm just putting it in as a separate thing. If you cannot get it out, don't worry about it. I'm just saying that there is a connection there. So there's one caveat. I wrote here this conservation of energy and momentum in general relativity with a derivative here. In real life, it's a more difficult type of derivative that's called capital D. And the definition of that thing...
Do we want to know?
Yes, well, you should actually, but I can say one small thing about this. This is called the covariant derivative. And that's defined as the usual derivative plus a connection plus this thing. The reason is that if you have a curved space-time, what a normal derivative does is tell you how functions will change if you move through space. Right? It's f as a function of x. You go one step in x direction, how much has your function changed? That's what a normal derivative tells you. But now you have a situation where not only your function changes, the space on which you are moving also changes. So that means there's two reasons why the outcomes of your functions change. One because of the space-time in which you move, and one because of the function itself. This is the space-time change. And this is the changing of the actual function. So it's called the covariant derivative, and there's all kinds of mathematical reasons why that thing exists. And no, you don't want to know maybe. I'm not going to go into it. Long story short, I'm just saying if you have assumed this, this is already implicitly assumed. But we're going to put it in as a mathematical assumption. Well, let's just put it into the Friedmann equations to see what happens. First Friedmann equation, a dot over a squared equals 8 pi g over 3c squared. Then there's rho, and our rho is going to be energy over a to the 3. And I said, well, let's take the situation where the space-time itself is flat universe, so k is 0. Here's one equation. Here's the second one. Minus 4 pi g over 3c squared. Then there's rho again. Plus 3 times p, but p is 0. So these two equations I have to solve. And then hope for the best. Let's see if we can find a as a function of t given this. Any suggestions how to do this? Here's where the actual exercise begins. It's a mathematical exercise. It's very little physics from this point on.
I haven't tried yet if it works, but I tried to write an expression for a dot and then say that a dot dot should be the same as the ADT of a dot, and then try to work that out and plug them together, but I don't know if it works.
I think this missed a step in the middle. You said you took this one?
Yeah, so I took the first equation and I tried to find an expression for a dot.
Okay, so you wrote this as a dot equals something?
Yes, well, I tried to, I didn't finish it yet.
Okay.
But then with the second equation I wrote something like a dot dot equals dot dot dot.
Yes.
And then I said that in fact from the first one that we wrote, so a dot. The time derivative of this one should be the same as the expression for a dot dot. And then
Oh.
set the time derivative of that one equal to a dot dot.
Okay, I understand. So you from this one you take an expression for a dot
Yeah, exactly. And then I take
Yes.
the time derivative
of this one, and what it should give you back is a dot dot. And so you set that one, what you got out of this one.
equal to
To this.
8 times
Yes.
the right hand side.
Okay, well, let's try that. I mean, it sounds like a sound mathematical way of going through this. So let's do that. I had a different method in mind, but well, let's see what we get.
Yeah, I don't know if it works out.
Well, we will find out now. So here's her idea. First, she multiplied everything by a squared. So you would get 8 pi g 3c squared with some unknown e over there-ish. You have multiplied everything by a squared, so it gives you this. Right? And then take the square root of both sides. And here is her expression for a dot. And now Panos, did you have a question, by the way?
Oh yeah, not really mathematical, but are we modeling the matter as a gas? Is that what you were saying
Yes.
earlier?
Yes. I'm sorry, I mean, you put up your finger and I sort of forgot. Sorry. Okay. All right, so we have a dot here that comes from the first Friedmann equation. And then Liz's suggestion is take the derivative of that thing. So you get a dot dot, and hopefully you can connect it to this one and see what you will get. Well, let's do that. You haven't followed this program through, I think you said. So we have to find what happens. So what's the derivative of this thing with respect to t?
I haven't calculated it yet. But,
Well, let's do it right here, right now. There it is. Right, this is just a constant. So I put that one there. Then I have a derivative of a square root, which is 1 over 2 times the square root. That's this thing. Chain rule says then take the derivative of the thing within the square root, which is 1 over a. This gives you 1 over a squared. And then another application of chain rule says then take the derivative of a itself, which is a dot. So this should be it. This is just a derivative taken. There's no higher mathematics going on here. See if we can clean up a little bit here. 8 pi g. Really curious what will happen. There's a 2 here, which corresponds to a 4 here. Might as well write a 2 here. So I've got rid of this 2 there. 1 over a goes upwards, so I get square root of a to the 2. Here's a minus, and there's an a dot. I'm doing this real time, so if you find any mistakes, please let me know. Something like this. Square root, and there's a 1, 3, 2, a dot. This is it. This is a dot dot, what we have found. Right?
Yeah, but there's still an a dot in there, so
Yeah, well.
that's probably not gonna work.
Well, you know, how about this?
Ah, okay, because then we can just go and plug the first expression back in, like
Yes.
the square root of that.
Yes. Uh, 1 over a 3, 2. Here's a dot over a. And I did that deliberately, so I can now plug in this again because I know an expression for a dot over a, which gives me 8 pi g 3c squared square root. Here's an e over 1 over a to the power 3, 2. Right? Okay, so that gives me minus 16 pi g 3 c squared. That's a 4. That's interesting. This gives me 1 over a to the 3. So I get this now. Okay. That doesn't help us. It just gives us back what we already knew. So we just found the second Friedman equation again. It's too bad. It's correct though. I mean, we get something back that is physically true. This is not something that will.
To be expected.
Well, of course, yes. Yes.
Sorry about that.
No, that's fine. It's fine. Again, these are nonlinear differential equations, right? And I told you before that nonlinear differential equations don't come with rules that always work. You have to find your own rules every time that you find one of these. So we have no choice but to just go and try stuff. So it's not wrong. It just doesn't get us anywhere. Here's my suggestion. I'm going to erase this, by the way. I have a suggestion. And if that one doesn't work, I have another suggestion. We'll get there eventually. What I notice is that this thing and that thing are only a factor of -1/2 apart from each other. If I multiply this thing by -2, I get this thing.
There's a square.
Yeah, so I see no problem.
Okay.
I'm just looking at the right-hand sides.
Oh.
If I multiply this one by -2, then this becomes a times plus a times g pi 3c squared. Then I have to also multiply this by -2. I have now two Friedman equations, and both have the same right-hand side. So that means the left-hand sides must be equal. So I now have something that contains only a's. In fact, it contains a little bit less a's because I get a dot squared over a equals -2a dot dot. I've just multiplied both sides by an a. Now before we try to solve this, I've just combined the two Friedman equations. Before we try to solve this, note that my solution, whatever a as a function of t comes out, does not depend on E, on the amount of energy. You see that? That's interesting. Apparently, if I want to know how this universe will evolve in time, I don't have to put in how much energy there is in a certain volume, just that there is energy in a certain volume. Whatever told me how much energy was in there, the E, that one actually dropped out. That's interesting, isn't it? The only thing they're making use of is that the energy density, the amount of energy per cubic volume, goes as 1 over a cubed. But how much energy there is in that cube of volume doesn't matter for the outcome. That's interesting. I think that's an interesting physical fact. All right. So we have a function, and if you take its derivative and you square that derivative divided by the function itself, it should give you back -2 times the second derivative. That's a differential equation. What function a is a function of t will make this work? It's hard to do these ones, right? Again, no standard tricks.
Powers of e.
As in, like this?
Oh, no.
Yeah.
Well, we can just try it out. See what happens. So this is our guess. With some unknown number that's called small lambda. Let's see what happens. I remember as a student when I studied these things for the first time that I spent many nights, because I typically studied at night, just trying out multiple solutions to the Friedman equations. I refused to do it by computer. I really wanted to see what would happen if I tried this. And after 5 attempts or 15 attempts, you sort of get a feeling for which ones will work and which won't work. Again, there's no standard trick. There's really just make a guesstimate, estimation based on the guess and on intuition, and then hope for the best. Here's one guess. If you take its derivative, you get this one. And if you square that thing, you get this. And if you divide that by a itself, you just divide out a to the power lambda t, which equals lambda squared e to the power lambda t. So this is what your guess will give us for left-hand side. Question is, does that equal right-hand side? So this is left-hand side. This apparently, using your guess, is a squared e to the power lambda t. The same guess tells you that right-hand side, well, we're already done. Unfortunately, this cannot be done. I don't even have to continue. I mean, this thing is always a positive number for any lambda. So that one won't work. If I put the -2, I mean, we can also just go through the derivation. You do get a lambda squared, so that's good. You get this.
Also, just the factor 2 itself is bothering you.
Yeah, that also.
As well.
I mean, if you remove this, all of it, you get 1 equals -2, which is not correct. So that one doesn't work. But I can sort of see where the guess comes from. Because what we have here is that derivatives equal sort of themselves, right? And that might make you think of exponentials. Now here is something that I picked up just by having tried these things many, many times before. At the moment that you find that the derivative equals itself, then you're usually going to get lucky if you try an exponential. But what we have here is not a derivative equals itself, you have a derivative squared, derivative to some power that equals itself. And I've learned just through many years of practice that this is a good choice, a good ansatz, good attempt. Then hopefully find the number a in a lambda such that it works. It's not a strict rule, doesn't always work. But maybe you can already see what's going to happen here. I mean, the derivative of this thing gives you a lambda -1 squared that doubles the exponent. Maybe you can set it equal to this. So let's just go and try this. So this is a guess. Well, if this is the case, then a dot t will give you a lambda t lambda -1. Squaring the thing will give you square here, square there, and a 2 times here. And then dividing by a, which means dividing by a t to the power lambda, will give you a lambda squared t lambda -2. This is what left-hand side gives us, giving this assumption, this ansatz. This left-hand side, try right-hand side. -2 a dot dot gives you -2a lambda lambda -1 t to the power lambda -2. Hey, look at that. I'm not doing anything highbrow, by the way, I'm just taking derivatives here. Here's my ansatz. Let's guess that it's something like this-ish. Calculated the left-hand side, that gave me this. Note the power of the t, lambda -2. I also calculated the right-hand side. Look at that. It gives me another t to the power lambda -2. So that means that as far as the t's are concerned, this works. Let's put everything in. This should equal that. In other words, I should have a lambda squared t lambda -2 equals -2a lambda lambda -1 t lambda -2, excuse me. This is me plugging in the two sides. This drops out, that drops out, an a drops out, 1 lambda drops out, and I get back lambda should equals -2 lambda -1. And if I find the lambda that makes this work, then I found the right solution. Question, which lambda should I use?
+2. I think so as well.
Yeah. Okay. There you go. Okay, so apparently if you choose lambda this way, then this solution will hold. Regardless of A dropped out. So it should be proportional to t to the power 2/3. Good. We found a solution. In a universe where there's only matter, particles floating around, and you let that universe go through its motions due to general relativity, its scale factor will go to the t to the power 2/3.
Does this 2/3 have any relationship with the -1/3 in the exponent of the A, or is it just coincidence that we get it?
No, that's related. That's related. Yes.
Can you repeat your last sentence? Like what the significance of?
Yes, that if you have a universe in which you just put matter,
Yeah.
and by matter I mean stuff of which its density goes over 1/a to the power 3,
Yeah.
and no pressure, so it's very cold matter, it doesn't bounce around too much, then you'll find that general relativity will make that universe expand as t to the power 2/3.
But if you compare like the universe as a gas, and gas has like no kinetic energy, and it's not like pressing against
Yes.
something, like would it expand at all? Would it not just stand
Oh,
still?
yes, but you're confusing now expansion of a container
Yeah.
of gas
Yeah, yeah.
with the expansion of the universe. In the case of the
Can you
expansion,
compare?
they're very different.
Oh, okay.
No, because the expansion of a gas in a container or in a balloon or something like that is really because of the bouncing of the particle as against the side.
Mhm.
Now, first of all, there are no sides here.
Yeah,
There's no,
okay.
that's one thing.
Okay.
But secondly, that expansion is in a balloon, say, or in a barrel of gas, is the expansion not of the space itself, of the amount of meters within the thing. It's just that the boundaries are shifted. That is very different from making the amount of space bigger.
Okay,
You see that there's
yeah,
a
yeah,
difference?
yeah.
You can draw a picture of this, by the way. Here's the size of the universe, the relative size, 82 points in space, and you just wait how things will move. And it's this function. You know what the thing looks like? It's a mathematical question. Can you draw that graph?
Should be something like a cube root or something like that, squared. So like a cube root but all positive.
No, because the exponent is smaller than 1. So,
Should appear flat for the first few t's.
well, you know what? We can actually answer that question just by taking its derivative. Because if you take a dot, that's then the velocity with which the universe expands. That will give you 2/3 2 to the power of -1/3. Is this the derivative? Is this a positive or a negative number? The whole thing, for any given time.
Positive.
That's positive. So it's an expanding universe. How about you take another derivative? So you can tell how the acceleration of the universe is. Take another derivative, it will give you 1/2/9, and then it's 4/3. Question, positive or negative number of any moment of time? That's negative. So what we have here, that our solution tells us we have an expanding universe because the velocity of the universe is a positive number, but its acceleration is negative. So it will move outward, but the speed with which it does it will slow up, will slow down. Now if you go back in time, so at the beginning, here-ish, if you know that it's going towards something that isn't very slopey anymore, because its acceleration is going down, that means that at the beginning it had a high slope. and then it curves towards a plateau. Not a full plateau, it's not an asymptote, it will always keep on going up. Do something like this. So it starts, well, it's more pronounced maybe, it's probably something more like this. There you go. That's this universe. Yes?
Do we get it accelerating accelerate expansion because we didn't include dark energy in the
Yes.
equations?
Yes. The Friedman equations here, the second one, which tells you something about the acceleration, come with the minus sign. So whatever comes out, you will always get a negative acceleration, unless you do something special to this part. And this is where dark energy comes in, and that's the one of the exercises that I erased. You can find out for yourself what then happens.
So for that was the scope of the thought that the universe acceleration was slowing down. That was the prevailing.
Yes. And it was only until 1998 that they did the first measurements that gave an indication that things were speeding up. And then we did more and more measurements. They found that it was very conclusively so, and that got one Australian, 2 Americans, the Nobel Prize in 2011.
It's completely unexplained by the model because this is all there's derived from it. You have to add something external.
Yes. Yeah, there's two possibilities. Either you believe general relativity and therefore the Friedman equations, and you have to assume some strange type of matter or energy, one that makes this whole thing positive again, or you don't even believe these equations and therefore not general relativity, and there's something wrong with general relativity. And the standard practice of thinking about this is that the equations are correct, is there's just some strange matter thing going on or energy thing going on. But there's also a school of thought that says no. The equations themselves are not correct for all kinds of reasons. And it's a completely unsettled matter at the moment. Nobody knows what the answer is.
Just what is one of the